Hello, folks. My name is DanWebinar1. I'm a professor with the University of St. Augustine. As part of the university's strategic initiative to support faculty in their research interests, I've been asked to put together some webinars, and this is the first of such. So I'm new to recording this, but I will try to stumble my way through. So our topic for the day is going to be reading a summary ANOVA table, the kind of printouts we get after you do some statistics. And there's a picture of me. Sorry about my luck. But we're hoping that maybe this webinar would be used by guests, even potential students to the University of St. Augustine. So we welcome you to join us. I'm an associate professor in the EDD and the DHSC, but please contact us for any of our programs. There you see our 1-800 number and our web address. You're also welcome just to call up the school and ask for me. I'd be happy to chat with you at any time. So, to try to figure out what's going to be the first webinar, it's hard for me to come to the idea of where to begin. I thought about that passage from Lewis Carroll where the white rabbit puts on his spectacles and says, "Where shall I begin, please, your majesty?" And the king says gravely, "Begin at the beginning and go on until you come to the end and stop." It's kind of ridiculous. Actually, I have a little different story about where to begin. My son is in his late 30s now and has children of his own, but when he was about, I think he was in first or second grade, we were on a family trip with my parents, and my dad had a van, and you can tell how long ago it was. It had a CD radio, and he was letting my son play with the CB mic and sitting there in between Grandma and Grandpa, and he mentioned to my son, Ken, look at the airplane. The airplane was flying up in the sky in our front windshield, and Ken grabbed the mic, keyed the mic, and he says, "What are you doing up there? Are you messing around and eating bananas?" And that was such an unseemly thing for a little kid to say, and of course my mom thought it was hilarious, and being a little kid, he had to say it over about 20 times. But as to the decision of where to begin, I want to put that little story about what are you doing, messing around, eating bananas, and I'll come back to that at the end of this. Okay, so you read the research, and in various forms, when they finally get to the results section, generally for most parametric statistics, you're going to see something the equivalent of a summary ANOVA table or a summary analysis of variance table. This is the table that tells us how it is that variance in the study has been partitioned, and then ultimately it'll tell us whether that relationship was statistically significant or not. I come from a school of thought that suggests the idea that overlearning is a good idea. In other words, to learn something so well that it can be a point of reference for future things that we might do and study. So that's exactly what I'm going to try to do here. A little bit of overlearning on this summary table. And so for the first part, here's your self-test. Where did 30 sums of squares come from? And then, well, again, what is the sum of squares? Okay, so this is what we're after. To get there, I'm going to get to chat with you about BLEUs, or best linear unbiased estimators. In research methods and statistics, it is absolutely a fundamental idea. And I'll tell you right now that a mean, you guys know what a mean is, a mean is the best linear unbiased estimator. So here's our study. We have 10 students in our study, and there's their particular name. And we're interested in explaining the dependent variable student satisfaction. So there you'll see it in that column, that vector there, the 2, 7, 4. And the nature of the study is I'm interested in how much knowledge of achievement style could predict their satisfaction. So in this situation, satisfaction is our dependent measure. Achievement style is going to be our independent measure. And we're asking about the nature of the relationship. So this is a correlation, or more specifically, what we're seeing there, regression. So regression is just correlation with a line of best fit and some other goodies as well. So I'm going to tell you that the sum for satisfaction is 40 and the mean is 4. Okay, so let's move on. We can graph this. It's easy to do when you only have 10 students, 10 people. It becomes really difficult when you have huge data sets. But we can graph this so that each student in the study represents a place on the horizontal coordinate. And here we have, in the purple line, we have the mean plotted. So Sue got a 2, Jim got a 7, Mary's right on the mean with a 4. So you can see how this goes. And with these little squares, we can count units. How far a particular unit is from the mean. Of course, you know, what we're getting at is the idea of this is how much noise is in the study. We have to get to the place where we are able to work with numbers, and I'll show you how this ends up working. But first, let me give you a formal definition of what a best linear unbiased estimate is. If we look at the number of units above the mean, we'll find that it's moving from left to right. We got a +3, a +1, and a +3. So we have 7 units of deviation above the mean. And let's check the deviations below the mean. So we got a -2, -1, -2, -1, -1. We have 7 units of deviation below the mean. So that is the definition of a mean, and that is the definition of a best linear unbiased estimator, is that it draws the line such that it minimizes error. So let's say that the 11th and 12th person in the study was standing outside the hall, and we had to guess, what their student satisfaction score was going to be. Well, how this works in statistics is that in the absence of additional information, our best predictor would always be that blue. So for the next person, we would say 4, and the person after that, we would say 4. Okay, we can take the same graphic form and put it in table form. And so once again, here's our dependent measure satisfaction. There's the mean. And then we have the deviation or the units above and below the mean. Well, we just got done saying that a best linear unbiased estimator makes sure that it's the same above as below. So if you add them all up, surely you're going to get 0. Well, of course, we do this often in mathematics. What we can do is we can square those. So -2 squared is 4, 3 squared is 9. And when we sum up those deviations, the sum of the squares, so this is where you'll see it in the summary ANOVA table, SS, or sum of squares, the sum of the squares, we get 30. And ladies and gentlemen, this is where we get the 30 that shows up on the summary ANOVA table. We're going to talk about degrees of freedom and mean squared, significant, and during a later webinar. But for now, at least there we know where in fact that 30 sums of squares came from, or total sums of squares. All right. All parametric statistics, as you know, there are non-parametric statistics. Have trouble with that word. Non-parametric statistics are not based on normal distributions. With parametric statistics, all of them, and this is where I tell my students, please don't tell people just how easy statistics is, because you still make money doing it. But all statistics all parametric statistics have the form of being a ratio of some sort of signal over some sort of noise. Okay, you know where the noise or the variance is in this table, all right? And right here is our indication of how much signal or how much is accounted for. So again, ultimately, for example, that F is going to be the ratio of signal over noise. This is just not a mathematical nuance. All research has as its root metaphor the ratio of signal over noise. And of course, my friends in the rehabilitative sciences, just like myself in the social sciences, we got it tough. For the most part, the research the phenomena that we study is very noisy. And, what comes to mind immediately is low back pain. So just how many sums of squares, just how much noise can show up in a low back pain study. And then we always have to ask that question in juxtaposition with just how powerful are our explanatory devices. So my goal, the goal of the webinars that I'm hoping to do in the future is to share with you some ideas on how to reduce noise. Okay, it's a ratio. If we reduce the noise, we're going to get a higher noise to signal ratio. And we can reduce noise through both design conventions and math conventions. And then additional ideas as to how to increase the signal strength, again, through design and math. So once again, our question is how much variance in student satisfaction scores can be accounted for by our knowledge of student achievement style. I use SPSS. I just love this thing. I love it as much as the Moore's Overlander. It's so powerful. Back when I was doing statistics, we were doing it in the IBM punch card. So I am just so happy with what SPS can do. And one of the things it can do is give us a graph, relatively easy, of this relationship between this independent and this dependent measure. And it would look like that. All right, so we see some scatter around the regression line, but otherwise it's relatively tight. And you can see in the upper right corner, it's all the printout comes out. It's relatively small font there, but it tells us the R square is 0.669. Okay, R is a correlation coefficient, but R squared is our Pearson product moment correlation coefficient. This tells us how much shared variance is between achievement style and student satisfaction. Okay, so SPSS gives us additional output as well. Of course, it tells us what R square is. We can see that there in the yellow bracket. But we can also do it mathematically. So if we take our signal, we've accounted for 20.056 sums of squares, and our total sums of squares is 30. we can see that particular ratio is 0.669. So again, you know, if we were to actually do a study and we account for 66% of the variance in the dependent measure, of course, we're going to be minor deities. We're going to be famous. So that would be a pretty awesome thing to do. All right, so we don't want to make any student sort of mistakes. So we never want to confuse the effect size or the strength of the relationship, in this case being R squared, with the relative probability of the finding. Of course, this is what students make mistakes on examinations, and even though we tell them time and again, you cannot infer the strength of the relationship from statistical significance. But we just kind of beat it into them until they finally get it. So what we don't want to do is get a comment from Red. If you've ever watched that particular show, you know what Red's famous saying is. So we don't want to be guilty of that. So here we got the summary ANOVA. This is what the sums of squares for the regression coefficient achievement style. You know, I'm asking a question. We know where sum of the squares comes from for the total. It would be reasonable to ask, where does that come from? The sums of squares due to the regression. I'm not going to trouble you with this and think that, of course, when I was a student, we had to hand calculate all this stuff. So it had to do with, you know, finding these deviations and squaring the deviations and finding the cross products and squaring the cross products. But ultimately, it comes down to some algebra. And the algebra basically looks exactly like that. I got to tell you, though, that hand calculating statistics is not necessarily the same thing we're going to get out when we have something like SPSS to it. Mathematical algorithms that run SPSS, you know, are a lot of decimal points, and they're also some pretty sophisticated calculus. So it's doing a lot of things that back in the day we really couldn't do by hand. So thankfully for it. So here we have it, friends. If we didn't have that regression line right there, and all we had is the mean, we knew that the amount of noise that we had in our study was the equivalent to 30 sums of squares. All right. Now we have a regression line, and we've accounted for 20.056% of it. The only error that we have left is this, what's in the little orange line. So if this was Sue, was the first point, we went from error, Sue had a deviation of 2, now she has a 1. So if we count up all 10 subjects, the amount of unexplained sums of squares that we have left is I have a mistake there. I have 0.99, so it'd be 9.44. So we explained 20. We only have 9 errors left. That, my friends, is doing some science. And to quote my son, if we're not in the business of explaining new and previously unaccounted for sums of squares in our study, we're just messing around and eating bananas. So I'm going to wrap it up here, and so this is my first webinar. Drop me a note. Let me know if it served your interest. Drop me a note. Let me know if you have any questions. Drop me a note and say, hey Dan, if you're going to do this next webinar, why don't you do it on such and such? I'll do my best to comply. Again, this is part of the strategic initiative for the university in support of faculty research and hopefully also to be used by some of our students and guests who might come to the USA. Again,